Hello, today we are going to learn all about integration by parts and an alternate technique for integration by parts called tabular integration by parts. We are starting with a warm-up that has nothing to do with either of those. It just has to do with integration overall. In this problem, we want to use the higher order mathematical idea of adding a particular zero. So here we have something that doesn't look like it's going to work out very well at first blush, because if you think about having 1 plus e to the x be your u, you're lacking a du. But here's the magic, friends. One way of doing this problem would be to add e to the x and also subtract e to the x. So that's what I mean by putting in a particular strange form of zero. The part I just highlighted is equivalent to 0. And so that's legal math. You can add a 0 anytime you want. And then we're going to chunk this, okay? We're going to take part of this integrand as its own problem, and then the remainder of the integrand as a separate little piece. And from there we should be able to get it, my friends, because we can see that really all we have is the integral of 1. And then over here, it has the characteristic that we were lacking in the first place. If that's my u, my du would be e to the x dx, which lo and behold we have. So this is now fitting the form of du over u with this as my substitution cloud. And so we are good to go. We can say that this is just x. This is natural log absolute value of u. Technically, that is always positive, so the absolute value is technically not needed, but it is also fine to have, okay? So with that little warm-up problem, hopefully you're totally in the mood to do more math. This unit is labeled as techniques of integration. It also has some other little tidbits in it, like more sophisticated problems that use L'Hopital's rule. But I thought I'd put together this list for techniques of integration. We already know use substitution. We know how to integrate certain particular facts using things like power rule, reversing trig, derivatives, things of e to the u, etc. Like there's just some facts that we know that allow us to integrate. We can use some algebra of various sorts, manam danam, right? When you kind of split up something that has multiple terms on the top with a single term on the bottom and break that into little pieces. Using long division or synthetic division when we have a division in our integrand, either one of those depending on the problem. We could use some trig identities at times that might allow us to integrate in a way that otherwise we would not. Partial fractions we used back in the series unit, but also can be used as an integration technique. Using completing the square to fit some other integral. So we use a lot of completing the square to see if maybe we have something that turns into inverse trig, for example. And then today, integration by parts and tabular integration by parts. That's quite a lot of different ways of integrating that we already know. Now, integration by parts is actually the technique that allows us to undo the product rule in derivatives, okay? So when we take a derivative, by product rule, we have the first term times the derivative of the second. I'll write that with a little prime sign, plus the second times the derivative of the first. Okay, so if I were to integrate both sides of that, okay, notice on the left-hand side, I am integrating and also taking a derivative, so those would undo each other. And then over on the other side of the equation, I'm going to now switch out these primes to write d something. So u times the derivative of v, and then v and the derivative of u. And I could have that split into two pieces like we did with the warm-up, right? Just split up that integrand. Now, if we were to isolate this term, so I had u dv. Its integral, the integral of u dv. Then the other side of my equation would be u times v minus this part, the integral of v du. That, my friends, is the integration by parts formula, okay? So this is going to require that we look at our original integrand that's a product, and it will give us a way to deal with some of those problems where there's a product in our integral. So I look at my integral and I try to figure out one part of it could be called u, one part of it could be called the derivative of v. If I assign everything in the integrand to one of those two pieces, and I can figure out both what u and v are, then I can follow this formula and often knock it out of the ballpark. You know what I mean? Have an antiderivative. So let's do a few examples together. Okay, now when I write these for myself, and this has long been my habit, since, back in the times when we didn't have electricity yet, and I was learning calculus, I always make a little box like this, and I put u and dv kitty corner from each other. And then here I'm going to have the derivative of u, and then here I'm going to have the opposite. I'm going to integrate dv in order to find v. Okay, so the two pieces that get assigned in the integral are u and dv. In this problem, this is my u, and this part's going to be my dv, and I will show you why. So you always want to have something, ideally you want to have something for your u that gets nicer when you take a derivative. So I want to take the derivative of x and just get 1 dx, or just dx. That's nicer. If I had made the x dv, then I'd have to integrate it. It would become 1/2 x squared. That's worse. That's less simple. Okay? Now over here, I want to think, what is the antiderivative of cosine of x? And the answer to that is sine of x. In this box, you do not need to worry about having a plus c. Okay? That's going to be in the problem itself. This is sort of like scratch work, like our u substitution card. Okay? Now, our rule said the answer to anything where I have an integrand u times dv, that format, I could just follow this equation. So that's what I'm going to do. I'm going to think in my head, I need u times v minus the integral of v du. Hot dog. Now this is a good outcome because I know that this part is an integral I know how to do. If that part were not an integral I know how to do, then I would need to do some more thinking, or maybe I want to reconsider how I assigned things. Over here I'm going to have plus cosine of x, and I should have a plus c now that I've completely taken care of all the integrals. Okay, that's integration by parts. Okay, we're going to use integration by parts when we have products a lot of the time. Doesn't solve everything, it's just one of many techniques. Now this at first blush does not look like integration by parts, but actually it is. And it doesn't look like it because you might not think of it as a product, but there's like secretly multiplication right here. And also, if you've been paying good attention, you might have noticed that earlier in this unit when we talked about other things that were exponentials and logs, we did not integrate this. Okay, and the reason we didn't integrate it is we didn't know this yet. It's the way that it has to be done, okay? So in my box, I'm going to take a derivative going this way. I'm going to take an integral going this way. I don't need to worry about the plus c. Then, since I have something that is in the form u dv in my integrand, the rest of it's going to be u times v minus the integral of v du. That's what I'm thinking in my head. I wouldn't actually write this. I'm just writing that to communicate with you. I would have u times v minus the integral of v du. That's what I actually would write. Okay, now I want to look at that integral and think, does it work out? Can I do this? I can. Those make 1. So I have x, natural log of x. I want to get rid of those parentheses. And then I have the integral of 1 dx. So that's just minus an x and a c. Simple as that. Okay, so from now on, if you would like to just know the integral of natural log of x, you can commit that to memory. But it's easy enough to figure out. It takes like 5 seconds. Okay? Example 3 requires integration by parts twice. And I might know this because of this being here. Okay, so it's going to take a while for that x squared to dissolve away through integration by parts. So u is x squared, dv is e to the x dx. Now we're going to take a derivative here, and we're going to take an integral here. We don't have to worry about the plus c if we're in the box. then we're going to follow the rule. Okay, so that integral, which is in the form of u dv, no other parts other than that, is going to be equal to u times v minus the integral of v du. Okay, and that doesn't look great yet because that integral at the end, I don't know how to do that quite. Okay, so we're going to do integration by parts again. I am deciding to pull out the 2, and then I'm going to let u equal x, because when I take its derivative, that'll be a lot better. And then dv is going to be my e to the x dx part, so v is just e to the x. So again, within this, I have u dv as my integrand. Okay, so the first term from before still tags along, and this minus and this 2, everything after it is going to be multiplied by that minus 2. So u times v minus the integral of v du. Okay, so let's just make sure you're with me. This part is equivalent to this part. That's where I used integration by parts. Everything else was there previously, and it's important to recognize that the 2 needs to go with everything that comes from that highlighted part. Okay, so minus 2x e to the x. I've got minus and a minus, so this is going to be plus. The antiderivative of e to the x is just e to the x plus a constant. And that's that. So sometimes it's a little like when you do L'Hopital's rule and you need to use it more than once. Sometimes you can use integration by parts more than once as well. Now, we included within your notes this little list that I honestly do not use myself per se. But if you're struggling about which part should be u and which part is dv, just like with u substitution, you can actually choose poorly. So if you're doing a problem and you're like, oh, I thought this was supposed to be integration by parts and it's not working out, maybe you've chosen badly, okay? Maybe you need to reverse the u and the dv to the opposite chunks or something like that. So overall, a rule of thumb that I have read about on the interwebs is this idea that there's a hierarchy for what you would like to have as u. If natural log is there, that's a great choice for you. Second option, second choice for you would be inverse trig. Third would be a polynomial. Fourth would be an exponential. Fifth would be trig. This is a very loose rule of thumb, and as I said, I don't use it, but I thought I would mention it just because if you're kind of like spinning, like just spiraling around and you don't know what to use, that might help you get unstuck, just to think through in kind of a structured way, what should my u equal? All right, so an interesting question would be, all right, great, what if I go through that hierarchy and I only have exponential and trig? Now, the thing that's going to be interesting here is that both of these, when you take derivatives, just cycle around, okay? So we could, for instance, sit here and say, all right, I'd like to let my u be e to the x. That means my du is also going to be e to the x. My dv, if I have that as cosine of x, my v is going to be sine of x. And that's interesting because nothing got better, right? Remember when I said that the u, when you want to take the derivative of that, you want it to be something that gets better? Neither of these has the possibility to get better. So you have to be very clever here, okay? And I would encourage you to write a little small, and I would encourage you to write the original problem, okay? And the other problems we've done so far, that didn't really matter, that you wouldn't write this original problem down, but in this one it does. So here's my original problem. U dv's integral is going to be u times v minus the integral of v du. Okay, great. Now this did not get better. That is kind of the similar sort of issue from before. I'm going to follow this equals along. And the result that I'm going to put in the next phase of the problem is what I'm going to get if I let u equal e to the x and dv equal sine of x. if that's true, V is opposite of cosine. Whoop. And derivative of u is still e to the x. Okay, so right in here, I would have u times v. Sorry for the bad handwriting there, I just noticed that. Okay, u times v minus the integral of v. Oh, so v has a negative, so minus a minus, and then v du. Okay, and then we'll close our brackets. Okay, now I'm doing a terrible job right now of how I'm writing this. I told you that you needed to write the original problem, and then this whole thing. Okay, so now look at everything that I just highlighted. Remember, there's an equal sign right here. Okay, do you notice that this is the same integral as right here? That is the same darn thing, okay? So let's just take a second. I'm going to try to write this more neatly, okay? Okay, I just took a second to write that a little bit more neatly, okay? So this integral is right here. I just wrote it like in a different order, but it's the same, okay? This over here is my original problem, right? This part over here is my original problem. And then the minus and minus, I made that a plus, okay? So the black line is what we're working with. Now notice that the thing I'm trying to solve for is in two different places in the equation. So we're going to just take this term and add it to the other side. When I do that, I'd have two of them. And then if I want to solve for this original integral, which is what I was trying to do, I just need to divide through by 2. And then throw on my constant of integration. So my final answer would be 1/2 e to the x sine of x plus e to the x cosine of x plus a constant. Therefore, that is my answer. Okay? That's called a cyclical or a cycling integration by parts problem. Okay, I have some problems back here that if we were together in class, we would do as group work. I'm going to come back later in the video with answers to that. But for now, I'd like us to go ahead and learn about tabular integration by parts. Okay, so I'll come back to that. See, there's the answers, but we'll come back. Okay? And let's talk now about tabular integration by parts. The word tabular refers to a table. So sometimes it is nice to just organize your thoughts, and that is what tabular integration by parts allows for. This problem is one where you would have cycling repeating integration by parts, right? You would have integration by parts twice because of the x squared, okay? So given that I can see that I'd have to use integration by parts more than once, I might choose to use this table, okay? And I'm not really explaining why this table works, I'm just telling you about it. I personally did not learn this until I was teaching calculus, so I will tell you that means that you can get through all of calculus without knowing this, okay? This is really just an optional technique. All right, so what you do is you make a chart. D stands for derivatives, I stands for integrals. The last column is going to be an alternating plus minus, plus minus, plus minus, okay? So under the derivatives, I want to put the thing I would classically have picked as my u. So in this problem, it would be the x squared portion. This is going to be my e to the x portion, or e to the x dx if you want to write the dx, but it's a shortcut, so we can leave that off. And then in the plus minus, you always start plus. I love calculus, I hate calculus. I love calculus, I hate calculus. That's how it goes. You start with the love though, okay? Then you fill in the table, and going down the left-hand column, you take derivatives. And you keep taking derivatives until you get to 0. And then you fill in your integral column until that same level. Okay? Then you add a little bit more in the middle and the right-hand column. Then you take diagonals, okay? So this is my first diagonal. And what I do with those is multiply them together. So x squared e to the x was positive. Then I multiply these together. Minus 2x times e to the x. Then I multiply these together. Positive 2 e to the x. Then the next diagonal I get, everything's going to zero out. So that is the end of my using the table, and I write plus C, and this is my answer. Look how slick that is. That's slick, right? Okay, I've got one for you to try by yourself. Please pause the video and come back and see if you're right. All right, so this is what I have for my table. And then down below, I've color-coded which diagonal goes with each term. And that's that. All right, so in your notes, there's reference to a cycling integration by parts. This takes one of those questions where if you have both an exponential and a trig function, things are going to repeat. So like the problem we did where we had to add and we got a 2 and then we divided by 2. This video shows how you deal with cycling. My goodness, I could not say that. Cycling integration by parts with a table. And so if you're interested in that, great. We also feel very confident that this is not essential information for you. So up to you if you want to take a look at that video or not. It's linked in the notes packet. All right, so go back to that collection of 4 problems, and we would like you to try these on your own. If you just glance at the questions, you will see that they look similar, but they are fundamentally different from each other. So pause the video and then come back to check your answers. Thanks for hanging in there with me, and see you in school.